Right, thanks, Ran. So today we'll look at three of these concepts: polynomials, coding theory, and Algebraic sorts. And this is joint work with Shahar Lovett. So the organization of the talk is as follows. So pseudo randomness of polynomials, algebraic geometry, coding theory, and finally a summary of the results. Okay, so what is pseudo randomness of polynomials? Consider a uniform random variable x over fp. Now we know that expectation of e of x is 0 since x is uniformly random, where e of x is e to the 2 pi I x by p. Okay. So then you want something similar to hold for pseudo random degree d polynomials. You want expectation. So this is going to be the setting throughout. So I'm going to keep this part on the board. So we are always going to look at n-variate functions from f to the n to f, and we'll look at degree d polynomials. And important in this talk is d is fixed. And so now we want to say that what does it mean for a degree d polynomial to be pseudo random? Well, it means that every, so here f is fp. It means that every field value is taken with the same probability, right? And for that you need something like you want something like this to hold.
You're just saying that f fix is
the output is like very random. Yeah. Okay, so the degree is fixed throughout the talk, and but then so what happens if this is not random? So what happens if this is actually large? It means it's not random, so it has to be structured, right? So what can you say quantitatively about the structure? Oh, this is the complex, the unit circle. So it's e of 0, e of 1, e of minus 1. So e is a shorthand for e to the 2 pi I x by p. Right?
F is over the fp. What is a?
A is like some scalar phase shift. So for all a. So a is just a is an fp star.
For all a.
Yeah. So you want this to be small for all a. Right? Only then f of x would be like completely random function.
Okay.
Yeah.
No, you don't want it to be
You don't want it to be large. So
yeah. Okay.
I mean it's a very, so it's because if I look at probability f of x equals c, it can be captured as well, summation a e of a f of x.
But why do we take an exposure?
So that's how it works. That's this is what f of x equals c breaks down as.
Oh, okay.
Right? Because now if I ensure all of these are small, then only the trivial term a equals 0 survives. So it's like 1 by p plus, right? So that's why usually this is an equivalent way of stating. So what happens if it's large? Like, can you conclude some structure about f? And this is a central problem in algebraic geometry and higher order Fourier analysis. Okay, so again degree d polynomial d is fixed. So let's say it is like the bias is really large. So the reason I say it's really large is because this is like the variance bound, right? I mean, so there are like p random variables, and you would expect this kind of standard deviation. So in such a case, you can say that f is actually a composition of only one low degree polynomial, and in fact we know what it looks like, and this is the Weyl and Deligne bound. So they say that so if then right. So but this is like really this is like a really large requirement on the bias. It says that if your function is not of this form, then the expectation is very small, which means that if the expectation is large, f is probably f is then a function of just one low degree polynomial h of x. So we want to know.
You don't care here about constants, because usually you would need a big constant times p to the 1/2, right?
Okay, so I cheated here. So I should have written d over square root p, but just to put this in perspective, I had to drop the d, because I'm going to keep d fixed throughout, and p is going to vary. Okay, so my next question would be, what if I replace the half by something larger, let's say 10? Then can you say something? So can you say something like, well, then f of x is not a function of one h of x, but maybe c h of x's, c lower degree polynomials, and this
By low, you mean lower than d?
lower than d, yeah, because you cannot allow degree d, because then it's you can just write f of x is f of x,
Right.
and yeah, and you cannot say it has to be degree 1, because trivially it's a function of n variables, so it is really very large. So you're fine even if it's just less than d, and that seems to be enough for all the machinery. So something like this was proved by Greentown and Kaufman-Lovett. So they showed that so they did show something like this, where if f is not a function of, so I'm writing the counter positive on the board and positive here, just whichever view you like more. But then the c here has very bad dependence on d, k, and p, right? So k is this, and d is the degree, and p is the field size. But the nice thing is it's independent of n, right? But the dependence is Ackermann. So even logarithmically growing field sizes are not enough. It's going to break down. It's going to make it look trivial, right? Because trivially f is a function of n linears, right? It's an n-variate function. So c has to be much less than n to make any non-trivial contribution. But since the Ackermann on p is the dependence on p is Ackermann, so it's like really weak. So you want something more efficient. And this kind of a theorem is very important in higher order Fourier analysis. Okay, so next we are trying to make it more efficient in P, and so surprisingly we are able to remove any dependence on P, and so this is the main theorem of our work, and I would like you to compare this to the k equals half setting and c equals 1. So recall that when k was half, it was the 1 over square root p barrier, and then we saw that f of x was exactly a function of one low degree polynomial. So here it's saying that, okay, I'm going to go, so if k is larger, then this is what you have, like no dependence on field size, no dependence on n. It has to depend on d and k, but this constant is not that great. That's why I had to hide it. I had to write c of something. It's Ackermann. Okay, so proof outline. I'm going to show how you can almost get to a decomposition, but not quite. And so this part is very straightforward. So you have to basically play with the derivative structure. So if any part is not clear, I'm going to use the board. Okay, so you have this. You start with a low degree polynomial that is biased, like 1 by p to the k. All right. So you define the derivative in direction y. So it's f of x plus y minus f of x. Okay. So for fixed x, I'm going to look at the expected value of this random derivative in direction y. All right. So Yeah, so I just expanded out dy of fx as f of x plus y minus f of x, right. Now if you see x is fixed here, so I can pull it out of the expectation, and what I am left with is just the expected value of f, right, because x is fixed and y is random.
We assume something that it's irreducible f?
No.
Because what if f is divisible, if it's divisible by x1 minus 1, then already it will be 0 with probability 1 over p just because of x1.
Yes.
So if it's x1 minus 1 times x2 minus 1 times something.
Yeah. So then it is a
2 over p. So this is biased, right? With probability.
Yes, but it is a function of few. It is a function of just two.
I don't care, right? N times another product, but this would be of degree d minus
Yeah.
2. We
Yeah.
just want that each of them will be
Just less than d. Yeah.
Less than d.
Yeah. So then this would be a function of x minus 1, x minus 2, and this other thing. So 3. So it's very low rank. Okay, so for fixed x, we have this thing is equal to something fixed times the bias of the function. Let's call it mu. So we have this is equal to mu times e to the minus fx, right, where mu is the bias of the function, and we know that mu is large, just to keep it in mind. So if I just rearrange stuff, I get e to the minus fx equals this. So it's kind of a recipe of computing f of x using lower degree polynomials. So we are not quite there yet, but it gives you an idea, like this is how we are going to cook up f of x's value by looking at these lower degree polynomials. But again, this is too much. There are like too many derivatives, right? So first step is to approximate this, and you'll just do some kind of Chebyshev inequality. So we are going to approximate this by capital N random derivatives and just taking the average, right. So my new recipe of and mu is large, so we can allow some kind of larger error in our estimate, like inverse poly in P, and also there is resolution in between the like two consecutive E of A and E of B. So finally we have f of x is
Wait, what is the previous time?
this one. Oh, it means that two E of A and E of B are like at least 1 over P apart.
Why?
Oh, so you're asking like
What is A1? Just do this.
yeah, like two of these
Okay.
complex numbers are at least 1 over P apart. So you need some kind of resolution, right, to figure out what I'm closest to, because the way I'm going to guess f of x is it's the largest, it's the A that minimizes this value, right. I'm going to compute this expression and I'm going to see, well, which E of A am I closest to, and that's going to be my f of x. Right. So this is giving you a way of computing f of x for a fixed x using capital N many lower degree polynomials. But there are problems. One is that capital N is poly in P to make the Chebyshev argument work, but which is too large. You need something independent of P. So to fix it, we are going to choose a random fixed dimension subspace and choose all the yi's from that subspace. Okay. So if the number of yi's you need is like let's say p to the s, so now I'm going to pick a random s dimension subspace and basically take everything in A.
But what about the problem that just computes it
Exactly.
most of the points and not all of the points?
Right. So then what did we gain? We are still taking poly P points, right? But we gained in the structure. So we're going to use that later. So he's right. So he's saying that, well, even if you take everything in A, it's still P to the S, right? But now those yi's are more structured. And the way that helps us is, so you can show that only constantly many dyis determine the rest of the dy's. So technically you are taking all these, but you can show that there is a special interpolating set which is constant in size, such that if I know the value of f for all y in S, everything else gets fixed. So there is a lot of redundant dy's.
I was actually asking before that even if I allow dependence on P, this just gives me something which is correct on most.
For most, yes, yeah. So that's another problem, right? So, but even with all this, what we have achieved is for a fixed x, this statement holds with high probability over the yi's, right? And therefore, for some setting of yi's, we have this probability over x, right? So we have almost solved the decomposition, but only like high probability over x. We still don't have exact computation, right? So this is the first step of the proof, and so the next step is to basically get this to exactly equal to 1, and so I'm not going to present the proof here, but it requires some higher order Fourier analysis, which I'll introduce later, but for some other purpose. But it follows the proof structure of green tau, from here getting it down to equal to 1, and basically you are going to ultimately have f of x equals this for all x, right? But these are the starting polynomials you work with, these derivative polynomials. You are going to make more refinements as you go on and make it this near miss result into an always correct result. Okay.
What would be the dependence? So how many?
What is capital N, you mean?
Uh-huh.
It's going to be Ackermann in D, and K. K is the bias, like 1 by p to the k.
By Ackermann, you really mean Ackermann, or in the Ackermann hierarchy?
Well, the tower bound is a like very weak lower bound.
Okay, is a second.
So it's much worse than a tower bound. So
for small, so if D is
even if D is like 3, it becomes like doubly exponential. No, for D3 is exponential, D4 it's
this is much less than tower. So when does it get more than tower?
So I think when you hit D equals 5, you get a tower in K, a tower of length K. Yeah, and it's already very bad there.
Okay, but it's probably, so it's not Ackermann function, I think. It's something in the Ackermann hierarchy. So for each.
Yeah. Right. Yeah, you're right. For lower D, we are still good, but yeah, we are in that range. Okay, so this is going to be the central theorem, and now we are going to look at some applications in algebraic geometry and coding theory. And so I'm going to keep the central theorem here, and then I'll move to the applications. So if this is if it's biased by more than 1 by p to the k, then f is a function of a constantly many low degree polynomials where c is dependent on d and k. Okay. All right, so let's look at a Nullstellensatz set. So the Hilbert Nullstellensatz set. So you have these k polynomials of degree d, and then you have another polynomial h of x. And h of x is given to be, the promise is h of x vanishes on the common zeros of fi's. So then there exists integer r, so there exists integer r and d, capital D, such that you have these multiplier polynomials g1 through gk such that this holds, right, summation fi gi equals h to the r.
The field has to be algebraically closed.
Okay. So the usual, so like Noga pointed out, on in the usual setting, you want a stronger assumption. You want that h of x vanishes on the common zeros of fi x in the closure of fp. Okay, that's the actual. But so we would work without that, and we'll see in the next page what the results are. So the idea is to get bounds on r and capital D. Okay. Well, as I say, tell you about the results, I'll say which ones require the stronger hypothesis of closure 0 and which ones require just the finite field analog. So I'm going to assume the number of polynomials is fixed. Okay, so the first result is by Herman, and she proved like capital D is doubly exponential in n, and r is some constant depending on d, and there you really want, you are working in the closure. And so then Brownowell and Kohler in a breakthrough work able to get it down to singly exponential, and they proved that capital D is just d to the k and r is some function of d, again in the closure world. So Green and Tao worked with a finite field analog, saying we don't need it to vanish on the closure as long as h vanishes only on the common zeros of fi's in the field itself, then you can actually get something very strange. You can get r equals 1, but you lose here. You get d to be something which is Ackermann and d and p, but you get r equals 1. So the moment you get r equals 1, you immediately get an ideal membership algorithm. Like given f1 through fk, tell me if h is in the ideal of the fi's. So you can get an algorithm that runs in time n to the this, right? Because all these two would give you radical membership algorithms, but
I don't quite understand. I mean, so sometimes it's just not true with r equals 1, right? Or what?
well, okay. So the counterexample that you're trying to say is something like, well, what if I say that this is x square and my h is x. Okay, so then the promise is that whenever this vanishes, that's true. But can you write this as can you find multipliers gy such that h of x is equal to f1 g1? So the way to get around this is they have p here. So they're going to use the fact that x1 to the p is x1. So I'm going to choose my multiplier to be x to the p minus 2. Okay.
What is C of D and P?
What?
Did you tell us what is C of D and P?
You mean what this function c is?
Yeah. What are the dependencies?
So these are like very efficient. These are like d to the k. K is fixed, so these are like poly d.
Okay.
But this is like in the previous result. It's worse than a tower of length d and k. So you can have 2 to the 2 to the, and this would have maybe, so even this is a lower bound, so it's worse than this. So it's more like it's an asymptotic result in the truest sense, like it's and here p also enters the picture, so this also has p.
So the point here is that r equals 1?
The main point is that they are able to get r equals 1, which immediately solves the ideal membership problem. And right, and so we are able to basically get the p out in a linear way, and this is tight because of the example, you have to get p, but this is the shape you expect, and you have p times c of d, and you still have r equals 1. So, you can still solve the ideal membership in time n to the capital D, right.
So this is equality as function, as not as polynomials, right? Like, because you said x to the
It's
p
as
equal to
functions on fp, yeah, right, as evaluations. So mod xi to the p minus xi's for all, yeah. Point. So and there are like other applications like this in like counting points in rational varieties and holes in the number of points in varieties and so on. But I'm not going to go over them right now. So I'm going to jump to another application, so coding theory. Okay, so just an introductory slide on codes. So codes, you have what is a code? You have an ambient space, you take a subset in it, that's a code. But and the way it's different from any other subset is you have two parameters that you care about. So the rate and minimum distance. So the rate tells you how many of these code words you have. So what is the size of your subset, and minimum distance tells you that, well, how far apart are each one of them. You want them to be as far as possible from each other, and at the same time you want a lot of them. So kind of like contradicting. Okay, and what is list decodability? Well, it asks for the number of code words in a ball of radius r, and you want to show that it's bounded. Like, what is the maximum radius you can get to, and still ensure that the number of these black dots is bounded, right? That's the list decoding problem. So getting into more specifics, so the Reed-Muller code. All right, so here the space is the space of all n variate functions over fp to the n, from fp to the n to fp, and so your code words are basically low degree polynomials. So you can think of each point as a evaluation of the function. So you can think of it as a vector of length p to the n, and the distance between two functions is defined as the normalized Hamming distance between them. So distance between these two is simply probability that p1 of x not equals p2 of x, right. And you can show by Schwarzschild lemma that the minimum distance is 1 minus d over p. So I'm assuming d is less than p now, and just for the proof outline and presentation. So any two polynomials are at least 1 minus d over p apart, and this is tight. So this number is going to be important, the minimum distance, so we'll see that later. Okay, now that we saw what Reed-Muller code is, now what is list decoding of Reed-Muller code? So there's something called a list decoding radius, and what it means is it's the largest R0 such that if I look at any ball of slightly smaller radius, then the number of code words is independent of n. So what is the maximum R0 you can have, such that if I shrink the ball a little bit, the number of code words loses any dependence on n. So let's see what the list decoding radius would be. So let's look at a ball of radius 1 minus d over p and see how many code words we have inside that. I mean less than or equal to 1 minus d over p. So here you will have exponentially many code words, and it's very easy to see what the polynomials look like. So take any linear function of your choice and you look at Lx minus 1 dot 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 Lx minus d, right, and what is the distance of this polynomial from the 0 function? It is 1 minus d over p, right, and there are p to the n many choices of the linear form. So there are p to the n many code words that are sitting on the edge. But that doesn't rule out the fact that the list decoding radius can be this, because recall that the list decoding radius is the largest R0 such that if I shrink it, then the number of code words becomes independent of n. So what if I ask the number of code words at radius 1 minus d over p minus epsilon. Can you show that it is independent of n, right? So, in fact, people have shown that for a large number of settings of d and p. So, they have shown that, which means that list decoding radius equals the minimum distance. So, they have shown that at the edge you have exponential in n code words, but the moment you come down little bit it is independent of n. So, we have list decoding radius is the minimum distance. For the linear case, this was proved by Goldrick-Levin and Goldrick-Rubenfeld-Sudan, and for the binary setting Gopalan, Clive, Zuckerman proved it in 2008, and later Gopalan extended it to the quadratic case for all fields. So, this paper is heavily dependent on the field being binary, like the techniques, but Gopalan used some Fourier analysis and he was able to prove it for the quadratic setting for all fields. And in an earlier work with Lovett, we were able to resolve this for all fixed d and p. So, for as long as these are fixed, you have list decoding radius equals the minimum distance. And over large fields there are a lot of results, but they all seem to point to the conclusion that list decoding radius is at least this number right here, 1 minus square root d over p. So, this is like called the Johnson bound, and all these results say that, well, if the ball is of radius 1 minus square root d over p, then I can output all the code words in it efficiently and so on. And people did not know what happens beyond this, and we know that 1 minus d over p is the maximum you can get to, because there are all these code words lying on the edge. So, there is this gap from 1 minus square root d over p to 1 minus d over p. So, in this result we actually show that we can go all the way to 1 minus d over p, again for fixed degrees. So, we show that even for large fields you can list decode up till 1 minus d over p, which is the maximum you can do, and it is algorithmic as well. So, so I am going to give a proof outline for this shortly. Okay, so we saw what happens at 1 minus d over p, or the minimum distance of d comma p. But what happens if I increase the size of the ball? So what if I want to know how many code words are in a larger radius ball? Like, so fix some e less than d, and you look at a ball of radius 1 minus e over p minus epsilon, right? Then how many code words do you have? So, you can actually show that you will have at least these many code words sitting in a ball of this radius. And again, a a proof for this would be to look at polynomials that look like this. So take your first variable x1, you construct this form x1 minus 1 dot 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 x1 minus e, and then keep another variable spare, and then you set any degree d minus e polynomials in the remaining variables. And if you stare at it enough, you will see that, like, the distance of this polynomial from the 0 function is slightly less than 1 minus e over p. So, you have all these polynomials sitting in this radius, and how many of them are there? Well, how many degree d minus e polynomials do you have? You have these many. So, this is the lower bound you have, and you want to prove something like this as an upper bound. So in fact, an upper bound of this shape was known for the binary case in a work by Kaufman, Lovett, and Porat, and in the fixed field, general fixed field case in an earlier work of ours. And in this result, we are able to extend this to general fields, right? And so in this work, in an earlier work, we actually had 2 to the Ackermann in p comma d comma s. So in this work, we are able to pull down the p to its right shape. So now it's p to the whatever remains. And as we saw, the shape of n is the right shape and shape of p is right. So an open problem would be to fix the shape of S and D.
Wasn't work by Amir
Over F2, yeah. But over F2, these this work already gets like an exponential in D bound, and Amir Spilka et al. Their result makes it exponential in E, or because E is less than D. So, and they really wanted that for their result. They wanted something that only depends on E and not on D, because what if I'm interested for E at E equals 1 or 2? So I don't want any D dependence. But all that is like they are all extremely good bounds compared to what we have right now here, at least for the general field case. So for F2, all the results are like the bounds are very good, like poly and exponential things. I mean, you see all the time. But in the general P, even for the fixed, we have this problem of bad constants. Okay, and just as an aside, a direct corollary is that we now have a better idea of the weight distribution of Reed-Muller codes. Basically, the number of code words at weight 1 minus E over P minus epsilon is exactly this. So you see kind of nice jumps in the number of polynomials. So you start with E equals 0. So that's like allowing everything. So then you have D minus 0. So you have all the polynomials. And as you keep increasing E, the number of polynomials keeps dropping until you lose dependence on N, and that's when you reach 1 minus D over P. So when you substitute E equals D, you get like you don't get any more N. So it tells you where the number of polynomials keep jumping. So we look at a proof outline for this. Okay, and we are going to set D less than P for now, just for the outline. So this is the goal. You want to show that the number of code words in a ball of radius 1 minus E over P minus epsilon is this number, P to the N to the D minus E. So the proof at the high level is a two-step proof. So given a center G, now construct a ball of 1 minus E over P radius. So the first step is a weak regularity lemma. So you basically replace the center G by a low complexity center G prime, which is more structured. So you get a set of low complexity proxies G prime for G, and low complexity means it's made of few low degree polynomials, and essentially it looks like this. It's a composition of constantly many low degree polynomials. So instead of working with the center G, you work with the center G prime that looks like this structured thing. And the second step is to say that I'm going to go over these steps again in more detail, but just high level. And the second step is to say that any code word that is close to G will be close to G prime as well, because G prime acts like a proxy for G. And anything that is close to G prime is much more easier to analyze, and you can show that any such F is really structured. So there cannot be too many such Fs that are close to G in the first place.
So G prime is close to G or not?
No, that you cannot ensure just by a counting argument. There are way too many. So G prime is not an approximation to G. G prime just looks like G to the class of low degree polynomials. Okay. Let's see if the next slides make it clear. Otherwise, I'll use the board. Okay, so step 1, expanding step 1. So you have these code words which are low degree polynomials, and you have a center G, which is an n-variate function, and the proxy is defined as follows. So there exists these C of these code words which will act as a proxy for G, and what that means is, so whenever a polynomial P is close to G, close meaning this whatever radius we're interested in, then that polynomial is also close to a G prime which looks like this. So, but note that this is a bit misleading. G and G prime need not be close to each other. All this is saying is whenever P is close to G, there will be a G prime where P is close to G prime, and the advantage is that this P1 through PC are universal. They don't change with capital P. The only thing that changes with capital P is this composition function. But this is fine for us because it's a C variate function, so we are not unhappy about that. Okay, so that's the first weak regularity lemma. So it basically reduces the list decoding problem around a general center to a list decoding problem around a more structured center. And so I think I'll take this down now. And the motivation to reducing it to structured centers is as follows. So what if the center was the 0 function? Then you know that any f, so let's say E equals D. So we are looking at any polynomial which is close to greater than d over p. So let's say we are trying to solve at radius 1 minus d over p, which means that how many polynomials f do we have which are more than d over p fraction close to g? If g is the 0 polynomial, then f of x is the 0 function, just by short zipple, right? So which means that f does not depend on x1 through xn. Now if I change this to g of x1 through xc, so which is just a c variate function, then if I have this hypothesis, then you can show that f does not depend on xc plus 1 to xn. Again, by a simple short zipple kind of argument, you can say that f is actually independent of anything outside g, which means that the number of f which are close to g is small, right? It's just,
You're assuming that G is low degree?
no. That's why it's powerful. I mean, if G is low degree, then you have something stronger, right? Then f is the constant function, because f minus G is also low degree. I'm saying G is an arbitrary function, but G is only C variate. The only reason this can ever overshoot the legal limit is if f does not have any dependence on the remaining variables. F is also a C variate function, which automatically puts the number of such f's at p to the d. I mean p to the c plus d choose d, right? The number of C variate degree d polynomials. Right? This is one way of bounding the list decoding size when the center is structured. Now we almost have that. We have that we are counting the number of code words around number of these polynomials around this structured center, but we don't have x1 have, right? It's a number of compositions on c plus k variables. That's a lot, p to the k plus c, right? And the way you get around that is you somehow do an argument saying that these are all, they behave like individual variables. So if the left hand side is a degree d polynomial, you cannot have an arbitrary degree d composition. You will prove that even the composition itself is a degree d polynomial. So you don't have so many of them, you have the right number. You have p to the, and this is like very, very small compared to this because you have n in the left one. Right? You can show that even t has to be like a low degree composition. So that's how you get away from the doubly exponential bound. So how much time do I have? Do I summarize? Then I won't go through the. So I'm going to tell you the proof outline one more time, and I'll skip the higher order for analysis.
Okay, enough about 5-7 minutes.
Okay. So then let me tell you about two problems with this approach. So the first problem is that we can no longer work with degree d polynomials. We to get this kind of an conclusion, you have to get to a subcode of Reed-Muller codes, and the subcode is actually we are going to only pick. So we will change our definition of code. We will only keep those degree d polynomials which are also of low rank, which means that keep only those degree d polynomials that look like for some c. So we are going to work with that subcode, and the second change is that we can no longer get one proxy for every g. There will be a bunch of proxies like g1 prime, g2 prime, gk prime, and all you can say is p is close to one of them, and then basically you bound the list sizes around each of the green ones and add it up. So these are two main points of departure. To make it more precise, I'm going to skip a lot of slides. Okay. Oh. Okay, so complete proof outline for that is as follows. So first you reduce list decoding problem for the general Reed-Muller code to a special kind of code of Reed-Muller code, namely only the low rank degree. So we only keep those degree d polynomials which have this representation. So we'll fix a universal c and then say any low degree polynomial that can be written like this for a constant c, we'll only keep those, and that's our new code c prime. And so we also show that this does not mess up our analysis, because we show that most of the bad code words lie in this c prime. So the fact that we threw away a lot of these code words does not affect us, because there won't be too many of them around the ball. So we can work with this structured code, which is actually responsible for all the code words. If you see, all the counter examples were very, very structured. So like x1 minus 1, x1 minus 2, and we are going to keep those things here, and we'll say that the others don't matter. And now given any function g, an n-variate function, so there is a list of these structured proxies g1 through gc, such that whenever any f in c prime is close to g, it is also close to one of the gi's. And finally we show that list size around these structured gi's is easy to bound by generalizing this short zipple kind of argument, and then you combine everything together, and that's how you have the. So yeah, that's an outline for the proof. Okay, so take home message would be like the notions of structure and pseudo randomness have a lot of applications, and just to recap, it says that whenever a function of n variables is biased, it implies that it's not really an n-variate function, but it's almost a c-variate function for a constant c. But I'm lying a bit. I mean, it's not c variables, but c low degree polynomials. So you can do this kind of dimension reduction as long as you're happy to work with low degree polynomial instead of linears. Like linears would be too good to be true, but if you relax this in the dimension reduction, then you get from n to a constant. And this kind of dichotomy theorems they have been used a lot. In this work we saw how to apply them in algebraic geometry and coding theory, and there are many other areas where they have already been applied. And so open problems, the first one is basically improve the bounds on D. because right now they're Ackermann, and something polynomial or even exponential would be great.
There are no interesting lower bounds.
Not in this algebraic setting. I mean, there are in the graph theoretic,
Right.
like triangle. I mean, there are people already shown the tower bounds, but here we don't yet have one. But this regularization technique, you have to avoid that. I mean, otherwise you'll keep incurring an Ackermann loss. Right, and the next, so a computer science open problem would be to extend this result to Reed-Solomon code. Reed-Solomon codes are essentially one variable, so degree d, but over one variable instead of n variables. And can you decode up till that 1 minus d over p radius? Right now we know how to decode up till Johnson radius from Guruswamy Sudan's work, but can you beat that? Can you go all the way to 1 minus d over p? So right now we showed this only for Reed-Muller codes, and that would be a very nice open problem. So yeah, that's it. Any questions or any